Okay, just as we were introducing ethers last time, we're going to go ahead and continue with a little bit of information about these. Keep in mind that ethers cannot hydrogen bond with themselves, but they can donate their electrons from the oxygen pretty strongly to things that can hydrogen bond. And that's sort of what allows us to use something called a crown ether. So crown ethers can they have a specific number of oxygens with some stuff around them, and they kind of act like as a cage, and different size cages will sort of hold on to different types of metallic ions. So that's what we use sometimes as well. The other interesting thing about ethers is that over time they can sort of go through what's called an auto-oxidation, and that can be quite dangerous or explosive. So we have to really watch out for old bottles of ether that sits around, and even an old bottle is not going to have very much of it in there, but it only takes a little bit because oxidative properties there could be very intense, shall we say. So to synthesize ethers, just to sort of recap a little bit of some stuff that we've done in the past, you could still do this with a double bond. We're going to do that with an acid, and so then the double bond would come and grab that hydrogen, leaving behind a carbocation. If you have an alcohol, that's going to find that carbocation. The conjugate base from over here would come and grab that hydrogen. Electrons go back, and bam, there we end up with an ether. But another way to synthesize a symmetric ether would be through just some acid. So this would be propanol with some acid, comes and grabs that. Another propanol molecule could then come in here and force that water molecule out, leaving behind the hydrogen. Another propanol molecule will come in there, and you'll end up with the dipropyl ether. This only takes a little bit of catalytic amounts of acid, and that's actually how we commercially make diethyl ether, which is most commonly what you know of in the lab as ether. Now, we've also got what's known as the Williamson ether synthesis, and this is going to use a sodium hydride. This is similar to the sodium borohydrides and the lithium aluminum hydrides that you saw last time, but it's actually even smaller. So this guy will come and grab this hydrogen, and electrons go back. So that's a way also to deprotonate any type of alcohol that you have, leaving behind obviously a very good nucleophile. This one then come in here and kick that out. Now this is an SN2 step, which means that this guy needs to be either primary or secondary, so that's something to keep in mind here. Excuse me, and there is how you yield your ether. The overall would simply look like NaX and Rx. Alkoxymercurization and demercurization is also alkoxymercuration and demercurization. Let's say it correctly. Sorry. The overall is it's really not even something that I'm going to ask you to know the mechanism for, but there's a double bond here, and after using HGOAC and an alcohol followed by NaBH4, you would end up with an ether right here. Now, you can actually make an alcohol this way as well, so this is the Markovnikov rule. I think we talked about this earlier in the semester, but you can make this as an alcohol by simply adding, instead of ROH, adding water, and that will give you an OH right there. Okay. So if we're looking at how reactive ethers are and how they really work, most of the time what we're usually doing is adding some type of HX, so HCl, HBr. What this is going to do is first it's going to split the R group so that one has an X and the other one's OH. And if you have an excess amount of this with heat, you end up making the other one, so this guy, also end up with an X on it. So it's a way to make alkyl halides out of ethers, which is pretty neat synthetically. So here's what that mechanism looks like. Once you have the ether, it can come and grab the hydrogen, electrons go back, and then this guy comes in here and kicks out one half of the molecule. So now we have this as an Rx, Excuse me, I got the other ones backwards, didn't I? So that's not there, and that is there, okay? So this comes and kicks this out, and that leaves, right? So once that leaves, we end up with this guy right here. We've still got another one. This is already on Rx. And this guy comes and grabs the hydrogen electrons leave. That gives you, boom, this one comes in, kicks it out, and there's your other Rx. Okay, so you end up with both of them having alkyl halide properties to that. This can also occur in SM1 if it's a highly substituted ether, so it depends on how your reaction is looking for that. But phenol won't work because it simply cannot undergo an SM1 or SN2, so it's kind of an exception to that rule. Okay, next I want to talk about epoxides. Naming epoxides is probably one of the more difficult things to name that we name in organic chemistry, simply because there's two ways to name it, and sometimes people use one way and some people use another way, or mix in between the two. So the first way, so remember that epoxide looks like a triangle with an oxygen in it, right? Oxygen therefore gives us a little bit of difficulty as to how we're going to name it. The first option is that we call oxygen the substituent, and we list the number of carbons where the oxygen resides, and that's called an epoxy group. The second option is that we call this entire circle here, the triangle right there, we call that an oxirane, where the oxygen takes the first position there. So let's try using some of that. Okay. In option 1, this would be named 2,3-epoxybutane, because we got 1, 2, 3, 4. And the oxygen exists between the second and third positions. Here this would be 2-methyl. Oh, we can count from this side, right? 1, 2 epoxy propane. Here we've got 1, 2 epoxy cyclopentane. And finally we've got 1, 2, 3, 4, 5. So that's a pentane as well. We've got a methyl on the 1, 2, 3, 4 position. So 4-methyl 2,3 epoxy pentane. If we're going to label these instead as oxiranes, now it's a different thought process. We consider this triangle our oxirane, and we're going to name the substituents that are coming off of that. So this becomes 2, 3, because 1 is the oxygen, right? So it's 2, 3 dimethyl oxirane. This one would be 1, 1 dimethyl oxirane. There's not really an equivalent name for this that I'm aware of with an oxirane per se. This would be 2 isopropyl, 3 methyl oxirane. 2 gets the highest number, or the lowest number, because of the fact that I is before M in the alphabet. And we can prepare these two major ways. You should have seen that we can already do this with a peroxy acid. Peroxy acids, most commonly we're using MCPBA. You can see the structure for that right here. If you start with a trans alkene, you still end up with a trans epoxide, and if you start with a cis alkene, you still end up with a cis epoxide, although you can still have the different arrangements of that if applicable. And the other way that we did this is through a halohydrin. So remember, with an alkene, you can add Br2 and water, and you can end up with this anti-arrangement of bromine and OH. Well, if we add base, we can still make this epoxide, and here's why. Once we have that base, the base is going to come in and remove this hydrogen, and then that's going to make a very good nucleophile out of this oxygen. So it's going to come in and kick that out and make that bromine leave. Notice that this structure still stays that way. You could end up with your same retention of configuration in this format as you can up here. Okay, thank you very much.